My name is Jarrett Laddie, and this is the Physics 2 Lab 3 Visualizing Magnetic Fields. The purpose of this lab is to create a visual representation of a magnetic field to better understand them, and to observe the relationship between the magnitude of a magnetic field and its observation distance, and to use Biot-Savart law to compare distance-dependent measurements. So the key concepts that are going to be used are the Biot-Savart law, which can be seen here, and distance-dependent equations that were used to analyze the data taken. And a quick preview of the results is our measured N value was negative 1.8491, and our magnetic dipole mu is equal to 7.55302 amps per meter squared. This was the data taken in our physical experiment in which we used a small rare earth metal magnet and a magnometer on our phone to record the magnetic field strength at various distances, including some off-axis distances where we would go at a 45-degree angle from the magnometer in our phone. So the general setup for this experiment was the magnometer would be oriented in such a way that the x component of the magnetic field it was picking up would be 0. This would mean that it was aligned perfectly with the Earth's magnetic field, so it wouldn't have to be factored into our on-axis calculations. And then for the off-axis, we measured just first the magnitude of Earth's magnetic field, which in this instance would be in the y direction, again using a zeroed out x direction, so it was perfectly aligned with Earth's magnetic field. And then we would bring the magnet a certain observation distance away at a 45-degree angle and recorded that, subtract our measured Earth's magnetic field from that to get a true y component of the magnet's magnetic field. And you can see the line of best fit that was achieved through the data analysis that was previously mentioned. Some observations that were made during the data collection was when the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnometer moves closer to the magnet, the measured x component of the magnetic field increases. And like I previously mentioned, the magnetic field of Earth must be accounted for by running the magnometer parallel when measuring, and then subtracting the measured magnetic field strength from the recorded magnetic field strength to get only the magnetic field from our rare earth magnet. The data analysis that was built into the spreadsheet gave us a line of best fit of y equals negative 1.8491x minus 13.403. This can be pulled out, so we have an n value of negative 1.849, and natural log of k is equal to our y-intercept of negative 13.403, which gives us a k value of 1.51 e to the negative 6. And then we can use the equations, the magnetic field of the bar is equal to k r to the n, and the magnetic field of a dipole typically is mu naught over 4 pi times 2 mu, which is our dipole moment, over distance cubed. And so we set those equations equal to each other and solve for mu, assuming that r equals 1, so it can be neglected for all these calculations because 1 raised to any power is still 1. We simplify down to mu is equal to k times 2 pi over mu naught, which gives us 7.55302 amp meter squared. The script model to show our magnetic field starts with defining physical constants, so our mu naught over 4 pi, and creating a magnet object, and then putting in our calculated dipole moment for the magnet that we calculated earlier. Then we use the Biot-Savart law to create a function that makes the dipole at a certain distance when you're given your mu value and your observation distance r. Next, we create some observation distances, 2 of which are in line with the dipole moment of our magnet that we defined earlier, and 4 are perpendicular to that dipole moment. Then we create 2 arrow objects using our dipole function to represent the magnetic field on axis, and then 4 more arrows, again using our dipole function to represent the magnitude of the magnetic field at all of those observation points. The last part of the GoScript model just calculates the vector and creates an arrow for the magnetic field at the 45-degree angle at distance d away from the magnet, and then prints out all of the vectors that it's representing on the screen. Now, if you look at the model that is spit out, you can see our 2 on-axis vectors have a greater magnitude than our perpendicular vectors, which holds true, and that there is a symmetry around the axis that the dipole moment is on. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So the experiment was oriented to account for magnetic north by zeroing the x component. If it wasn't aligned with Earth's magnetic field, Earth's field would have contributed to what was recorded and it would have skewed our data. And what if you were able to stick two identical magnets together end to end and run the experiment again? How would you expect the measurements to differ? So this would increase the dipole moment of the magnet, which would cause larger measurements, but not necessarily cause the measurements to double.